Okay, thank you, Mr. Chairman. Good morning, everyone. So it's a pleasure, an honor actually to be here in front of such a distinguished audience. So it's also a pressure for me. So as I was introduced, I'm working for some time on, let's say, summarizing structural integrity topics. And today I will make here some overview of my research and of my team. Actually, I'm not working alone. And today I select this topic. So I will talk about local fatigue approaches, which is some, let's say, classic topic, but I will show how we are doing or how we are researching these topics. And our main goal is to make structural integrity analysis of equipment, of structures, of mechanical components. For that, I'm supporting always these local fatigue approaches. So this is a picture of my faculty, Faculty of Engineering from the University of Porto. I start with acknowledgements because I believe I will be the spokesman of a lot of people behind me. So I must acknowledge first my PhD students, also master students collaborate with the team. Also the institutions, my faculty, the national and the European funding institutions are also acknowledged. Very important for my team and for me are the international collaborations. So we have a lot of collaborations with, for example, colleagues from Spain, from the north of Spain, Oviedo, also from Poland, Wrocław University, also from China, from the University of East Science and Technology of China, and the other colleagues, groups across the Europe and the world. So my motivation for my research is to provide answers to the industry. So in our case, in our group, our research is much motivated by the industrial requirements. So in my team, we are providing answers to the industry. For example, my department, my team is very active in collaboration with civil engineering department, providing answers about structural integrity and fatigue behavior of metallic bridges. We are also involved in structural integrity of, for example, rack structures, also welded structures like pressure vessels, welded bridges, also pipelines, and more recently we are involved in rolling stock design, where fatigue again is an issue that we are also addressing. So this is the way we get funds for our research. So I will make my presentation according to these topics. So I will start with some introduction to the local fatigue approaches. Then I will show you some developments that we were involved in our team regarding these local fatigue approaches, with some focus on modeling fatigue uncertainty. This is one of our topics. Then I will refer some, so we are always trying to cover all the fatigue regimes, but we had some projects in the extremes of the SEN material characterization. So I will talk a little about ultra-low cycle fatigue. Then I will jump to a more recent activity in our team that has been very discussed in this week, in this conference, which is the ultra-high cycle fatigue. So we are doing some, let's say, activity in this, and I will show you some of most recent results that we are generating. Then I will jump to the structural integrity case studies, where we try to solve different problems, applying the local approaches. and also solving some problems of scale, because when we are analyzing large structures and we want to apply local fatigue approaches, we must overcome the scale problem between the size of the structure and the need to characterize locally the fatigue parameters. So regarding introduction, everyone here knows what are the local fatigue approaches, but just to give some background or basic information about that. So we traditionally, when we want to make structural integrity design or analysis and relying on design codes, we are often directed to the application of global approaches, which are simplified versions for fatigue analysis. And in this case, the stresses, for example, are nominal, which means that we are far from the hotspot where the fatigue damage will start or evolve. And these are the global approaches, which currently still is the basis for many design codes. Anyway, design codes are evolving, and some codes are already incorporating some approaching to the local approaches, particularly including some more local stress definitions like the geometric stresses or the structural stresses or the hotspot stresses. So this is, in my opinion, a way going to the local approaches. And maybe it's where most of us are working in our research. So developing local models for fatigue assessment using local fatigue parameters, which those parameters are more consistent with the nature of the fatigue damage, which is very localized in the material. So we are talking of using notch stress approaches, elastoplastic notch strain approaches. We are also using always the possibility of exploring fatigue fracture parameters to address short fatigue cracks or long fatigue cracks propagation. So this is a very wide field of possibilities that allow us to address fatigue damage, for example, into different, let's say, stages of evolution. For example, fatigue crack initiation could be one of the focus. Sometimes in other applications, we are more concerned about fatigue crack propagation. And sometimes we try to combine those approaches to get a full fatigue life prediction. So this is what I understand in my feeling. The issue that we start with material characterization, and then we need a fatigue model. And with that, we can predict the fatigue of a structural component. So that's what I call the transferability problem between the material and the structural component or detail. So that's what I will try to show how we are doing in our team later on in this presentation. So local approaches, as I said, most of us are working in that topics. So it's almost the world inside this. So anyway, I guess I believe that still we still have work to do. So there are still challenges to overcome in the local approaches. So there is here an exhaustive list of, let's say, challenges that we need to address. So complexity of modeling. So this is a problem when we are challenged by industry to give clear answers about, for example, structural integrity of a bridge. So can we go to the grain scale modeling to provide that answer to the industry? So this is a challenge, because if I'm going to the grain scale, maybe I will not provide the answer on the time I have to provide to the industry. Also, that will require very high computational resources that we must have available to provide the answer to our customers. So usually local approaches faces the complexity in modeling much more nowadays, which requires in parallel high computational intensity. This is so we need to characterize the material. So this is also we have also high data requirements. We learned this week that maybe in the future we will don't need to test so much because we can model the material starting from the molecular dynamics. So this is, in my opinion, a very optimistic approach. In my opinion, right now, we need a lot of testing to provide clear and safe answers to the industry. And when we are talking about real-world applications, we have this problem. What are the loading? Sometimes the loading is not well known. Okay, so if you are talking of a bridge, for example, this is the case where load history is also a problem. Then we also need to validate our models. So there are a lot of models available in the literature. So we can play with a lot of different models. Anyway, we need to verify to make tests in the end to demonstrate that, let's say, our framework for modeling, it is working. So full-scale testing sometimes, if possible, is a good, let's say, approach to give confidence to the customers. We have always the problem of the scale and localization issues when we start with in the material and you want to go to the structure. And sometimes our models are limited to the specific fields or, let's say, case studies or industrial requirements. Okay, so before going directly to the structural integrity case studies that I want to show you later on, I will go through first the modeling of fatigue uncertainty, and then I will talk about some research work on extreme fatigue limits. So, as I told you, our work has been done in collaboration with different partners across the world. So we started a collaboration about 20 years ago with Professor Cantelli and Professor Castillo from the north of Spain. They developed a very, let's say, a simple and powerful probabilistic model based on well-known waveful distribution, but for fatigue analysis. And the most interesting part was that this model is able to predict the full SEN field, not only the fatigue distribution for a given stress or the fatigue life distribution for a given stress or the strength distribution for a given fatigue life. It really predicts all the complete field. That was possible with the discovery of this function, the V function, which combines the number of cycles and the fatigue perimeter. So this approach was, is well known nowadays, but it was in the original idea of the authors explored just for the stress or the strain perimeters as we used to see our SEN fields. Then with our collaboration, we start to realize, okay, this is much more powerful than the original authors found. And actually, this can be applied for different and more complex fatigue damage perimeters, where, for example, mean stress could be included in the fatigue perimeter, or we can use, or we can play with energetic perimeters, or even we can use this model for multi-axial fatigue, using, in that perspective, multi-axial fatigue perimeters like the one we are seeing here, known from Fatem and Sossi. So this was immediately explored in different fields, in different materials. For example, materials from old bridges in Portugal with SWT perimeter, or multi-axial, let's say, fatigue with structural steels were explored. Afterwards, we were applying this, let's say, this field, this fatigue, I would say SEN field, but it could be different parameters on the y-axis. So we were exploring this to, for example, model the fatigue behavior of notch components, assuming that the fatigue life will be a propagation of a crack, and that crack propagation is a result of successive crack reinitializations across a crack path. So starting with the material model, we were able to predict the fatigue SEN field for the notch component. A next step to this analysis was, Weibull model was very early proposed for describing the fracture stress in brittle materials. So we can benefit from that Weibull model description with our new fatigue parameter. So this generalized parameter, we can benefit from the scale parameter, and we can approach the fatigue prediction using or accounting for scale effects or size effects. So this delta parameter could be, let's say, extended to this version, and then we will have our probabilistic model with this new perspective for the size effect. So that will allow us to predict the reduction in fatigue strength when the size will increase, and also the scatter reduction for the same size increase. So doing that, we start to model the fatigue behavior of some components, like at that time, I was working in the riveted joints, so we were modeling the fatigue behavior of riveted joints starting with the material properties. We start with simple, smooth specimens. We test those specimens, and we extract the reference, let's say, SEN field, probabilistic SEN field, and then using numerical modeling of the joint, we can, using the weakest link theory, we are able to predict the fatigue crack initiation for this welded joint, as you can see on the right. So starting with material characterization, we jump to the component prediction. So with this model, for example, we can evaluate, for example, starting with the fatigue parameter, in this case, a very simple strain range distribution over the surface of the riveted plate. We can, for example, get the risk maps for the plate. For example, any given stress range and a given number of cycles, what will be the risk of the failure of this component after this history. One of the shortcomings of, let's say, of the original model of the proposed by Cantelli and Castillo, well, actually, it was understood in the original version as a shortcoming. Later, we realized that actually it could be not so like that. So we can see here, this is the parabolic, let's say, SEN field, and this vertical asymptote seems to be physically inconsistent, okay? And the other way, the horizontal one is okay because it resembles the fatigue limit of the material. And we should expect, when we are talking of the full SEN field, like this sigmoidal representation for the material fatigue behavior in, let's say, when you are using a stress perimeter, fatigue perimeter. So, but after some considerations, we realize, okay, we can get so this model could be, let's say, a transformation of this one. So how can you do that? Simply providing a new fatigue parameter. So we can work with the maximum stress normalized by the material tangent stiffness for the cyclic curve of material, and as soon as we are going to the plastic behavior of the material, this normalization parameter will reduce significantly, and theoretically for perfected plastic material it will go to 0, and then we get this asymptotic representation. So anyway, in the end, this makes sense. This hyperbolic representation, we can use it to, let's say, to jump to this sigmoidal representation. So this was tried for existing data at the time. So for this case, for the pressure vessel steel, we start with data. In this with the maximum stress, and then we have here a vertical, let's say, range of test data of 2 times. And when we make the transformation I referred previously, we can extend this to 40 times. So we are retrieving or getting the parabolic representation of our SEM field as originally proposed by Fernandez, by Castillo and Cantelli. Okay, so these are some experiences regarding the generalization of the existing probabilistic model by Cantelli and Castillo. Now we were trying, to explore the extreme fatigue regimes, and one of the fatigue regimes we were exploring was what we call the ultra low cycle fatigue. Why this study? So this was actually an European project that was interested in this project. The objective was to investigate the behavior of, for example, pipelines and extreme loading conditions, those that appears, for example, under seismic actions. So in that case, the failure of the material could happen very early, before the 100 cycles. And for that, we believe that we are talking not of low cycle fatigue, classically speaking, but we have in this fatigue regime, as you can see here on the bottom fractured surfaces, we have a mixture of crack propagation and some dimple formation, which is typical from the static ductile failure. So we believe that when we are in this region, the low cycle fatigue traditional approaches like Coffin-Manson will not work properly. So, and this is already documented in the literature that Coffin-Manson will overestimate the fatigue life predictions in this very short time duration. So, we in this European project, we already published a book with all the data. So I'm just giving you a very I'm just opening a small window to our work, so you can find a lot of testing data. You also including full-scale tests, very rare, that you can benefit from this book. And we also play with different models. So we have played with, let's say, continuous damage mechanics coupled models to address this material, let's say, damaging in this fatigue regime, which is affordable because we are talking of 100 cycles, more or less. So it's possible to integrate the equations for that duration. But today I bring here a simpler model just to be easier to demonstrate to you what is the background idea of the modeling in this fatigue regime. So we, in this case, I'm talking of an uncoupled model that relies on a very precise plastic cyclic plasticity modeling. So this is mandatory, otherwise we will fail in our predictions. Then we make some post-processing using this uncoupled model just to try to anticipate what will be the crack initiation. So we found the shoe model, which was developed at time for just uniaxial loading, and Then we extended it for multi-axial loading using the SME boil and pressure vessel code formula for the equivalent plastic strain range. And then this equivalent plastic strain range appears already in the Coffin-Manson, but we normalized it by the fracture strain of the material. That means the strain range effect will be more or less damaging depending how far or near we are from the ductile fracture of the material. And the ductile fracture was also modeled using at the time, so it was already, time passed too fast, so it was already 10 years ago, but at the time we, for the fracture strain, we used the By-Wierzbicki approach, which defines the fracture strain as a function of the triaxiality and the load angle parameters of the material. So fracture strain is not the constant of the material. So for characterization, for the identification of the model, we will rely on two sets of tests. First, on the left, we will need to make static tests. Those static tests will be important to define the fracture surface, or the ductility surface of the material, where we have the fracture strain against triaxiality and load angle, and you can see that this is not constant for the material. And then we need to run also cyclic tests, ideally for different stress concentration or for different triaxialities, in order to identify our model constants. With that, we can achieve or reach some idea for, or new idea for the fatigue crack initiation in this fatigue regime, which is characterized by these surfaces. So we will have the SEN surfaces where we are adding an extra dimension, which will be triaxiality or load angle parameter. So we have a multi-dimensional, let's say, surface for fatigue crack initiation characterization. Okay, I will come later to this modified model for ULCF in the applications when I will show you some applications to pipelines. Now I will talk of more recent data. So here I can say, maybe I was thinking to remove this from my presentation because it is supposed that we should bring here some more consolidated work. Anyway, I take the risk and I bring here some very fresh results, okay, about gigacycle fatigue that we are working just for 2 years, okay, more or less. Anyway, I would like to share some advancements that we are doing. So I have listened this week. So it seems that I need to speed up. So, well, there are a lot of challenges when we are, sorry, now, there are a lot of challenges when we are doing gigacycle fatigue. So we have frequency effects, we have dissipation, notch effects, multi-axial fatigue, size effects, all of this we need to address also in the gigacycle. Otherwise, we will be very limited on the information we are generating. So we are trying to solve this step by step, okay? For the moment, we just have preliminary results. So one of the challenges that I never heard people discuss so much is about dissipation. So everyone runs the test perfectly without any issues. We don't feel that way. We always, when we change material, dissipation will be different and we will have heating that we need to control. Otherwise, our test will be rubbish. So we recently developed a thermal model that just give us information about dissipation will be an issue or not. And so we can use our test itself to get the damping coefficients of the material, and then injecting that in the heat transfer problem, we can get the prediction of the temperatures of our material. And we found that this is maybe a classical work, but for us was interesting to demonstrate that depending on the material, microstructure of material, damping will change with the applied stress in the material. So it's nonlinear, the damping coefficient with the stress that we must address in some materials. For other materials, we can use, let's say, an average damping to estimate the temperature. So using that, we were able to estimate the temperature evolution in the material before, let's say, doing a very comprehensive characterization of particularization of the material. Then the frequency effects. We all know that, and we are trying to get a phenomenological model that overcomes this issue. So we have here tests for a spring still for 20, 150, and 20 kilohertz. So we have here some influence of the frequency that we are trying to overcome with a more complex model or regression model, again back to the basic model from Cantelli and from Castillo. It's possible to change the V variable to a more complex one, in this case, for variables, where the frequency appears implicitly in the influence of the elasticity properties of the material. With that, so this is a more intricate model, but opens a lot of possibilities. We can get our SCN field for a wide, let's say, range of fatigue lives, and benefiting from different, let's say, sources of data. And of course, we are making a transformation in our fatigue parameter. Recently, we succeeded to get some multi-axial fatigue results. So this is our just preliminary results in gigacycle regime. So we're using cruciform specimens. And for that, we still have, okay, we have some valid cracking in the specimens, but we still have to work and to explore. Well, we will have here to face the, let's say, the frequency effect, and in my opinion, we'll have also to face the problem of the size effect. Okay, so now I will run over our case studies very quickly, just to give you some highlights. Sorry for being so running in this presentation, but the first case was the pipelines again. So in our project, we were able to run full-scale bending tests of straight pipelines and elbows. Elbows are in the book. So we were able to predict the fatigue behavior well with our model. But as I told you, we need to first model very precisely the elastoplastic behavior of the pipe. And the most important is to capture the plastic instability, because as soon as you get the plastic instability, your triaxiality will increase, the load angle will decrease. All of this will be in the reduction of the material ductility direction. So that will speed up the failure of your material. So we were able to improve the predictions regarding the overestimation of the Coffin-Manson approach. Regarding now, just a brief story about welded connections. So I started some time ago a collaboration with the United States, with Battelle Ohio Institute, with the group of Ping Shedong. And at that time, Ping Shedong developed the structural concept for stresses, which are, those stresses are defined as equilibrium equivalent with the nodal forces of the finite element model. In that way, the idea is to get some mesh sensitivity for the structural stresses definition. Integrating the crack propagation law, accounting for small cracks effect, and accounting for the stress intensity magnification factors for duels, typical on duels, we were able to reach a master SCN curve with a new definition for the structural stress, which accounts for the stress linearization, the loading type, and the size of the plate under analysis. With that, we were able to, to demonstrate that it worked for pressure vessels components. So the colored points were from my team. So this was a database that nowadays is the basis for design codes. More recently, we improved the model, including the multi-axial approach. We also developed some cross processor for ANSYS in this case that is open for use if you wish. And then we run a lot of analysis on all data regarding full-scale welded details of bridges. And that data was run for bridges because we believe that, well, the details are different from the pressure vessel technology. But again, we demonstrate that with 300 new results, the master curve concept works perfectly. So it could be also extended to other design codes for bridges if you wish. So finally, I'm almost finishing. So just to say, we have also this big problem that how to make the fatigue analysis of such kind of large structures. So we are talking of a multi-scale problem, but in a different way that we listened this week in other lectures. So we must address the full size of the bridge, but I'm supporting local models. So we need to go at least to the scale of the rivet hole, not speaking about this scale. So, and we are talking of a structure that is under very complex loading, trains crossing the bridge induce dynamic loads. And we at the end want to reach the stresses or the fatigue parameters at these spots. So the idea was to make, let's say, submodeling in different scales or different steps and using modal superposition. So this is the way to speed up our calculations. Otherwise, we will not be run the analysis in the real time. Of course, we have some local nonlinearities that makes the challenge even more higher. So sometimes we cannot solve our last submodel in the modal space. We need to run submodel in the time domain. So that will increase our computational costs. So this was explored in different applications like riveted bridges for example, in this case in Brazil, where some failures were detected. And with some, let's say, modeling mitigation costs strategies, we were able to demonstrate that that damage, local damage, would be expected for the bridge. Finally, the last case, it's the structural integrity of wreck structures. The idea here is to develop new design rules for these structures made by cold form profiles. This is not available in our European codes, okay? So they are prepared for hot roll profiles, not cold form. So, but the basic idea is that, okay, in order to get the proper prediction, we should use local approaches and very important account for residual stresses. So in this case, we solve by modeling the process of the profiles production in order to get the profile of residual stresses. And in that way, we are jumping from what we call an acceptable accuracy band for the predictions. So we are talking this this red crosses, sorry, were considering the residual stresses from roll forming. If we adopt, for example, residual stresses from press break profiles, which is not exactly our process, will not work so nice as we should expect. Okay, the conclusions are very simple. So I understand that the local approaches provide us very high flexibility in when we are interested in doing structural integrity. So we have in our team improved some existing probabilistic models to get a generalized application of those models. We are also extending the perspective for the SCN fields. And we have been so far successful in providing answers to the industry, different industrial partners. Just last slide. Of course, I was not able to talk about all we are doing. This is just some titles of papers that we published and highlight some keywords that maybe are the trends that we are following now. Maybe now we are very interested in reliability, intelligent and reliability analysis, and artificial intelligence, because testing is very expensive. We need to look forward to ways to address the costs anyway. Thank you very much for your time and patience.